Alright, so we've talked about measurement and reliability, and we discussed how when you take a measurement, you're supposed to record all your certain digits plus your uncertain digit. And we have a special name for those digits, and those are called significant digits or significant figures, depending on what book you get the information out of. The reason that we have to know how to identify significant figures is because when we calculate using our data, for example, if we measure out a mass and we measure out a volume and we solve for density, our answer for density has to be rounded. And there are different rules for rounding, whether you're multiplying or dividing or adding and subtracting. So the first thing we need to learn how to do is identify sig figs in a measurement. So let's take these rules and talk about each one. First one is pretty easy, and all it means is that any number that is not a zero, a non-zero digit, those numbers are automatically considered significant figures. So if you have a measurement of 127.34 grams, you don't see any zeros there. So every single one of these numbers is significant. So we would say there's 5 significant figures in this measurement. So that's the easiest and the most straightforward of all the rules. 5 digits there, 5 sig figs, because none of them are zeros. So that's the easy one. The second rule, we start to incorporate zeros. And this is one thing that I like to call the sandwich rule. If you have any zeros in between numbers that are already significant, then those numbers, those zeros that are in between, become significant as well. So we know because of Rule 1 that the 1, the 2, and the 7 are already significant because they're non-zeros. These 3 zeros are sandwiched in between 2 and 7, numbers that are already significant. So because of this sandwich rule, as I like to call it, they become significant. So 1, 2, 3, 4, 5, 6 significant figures in this measurement. And again, these are measurements. These aren't just pure numbers. These are measured values. Okay? If I was going to interpret these values, for example, the 127.3, because of the rule we talked about earlier, this device that was used to take the mass obviously is accurate to the 1/10 of a gram, and the 4 was a guess. And this measurement was accurate to the 100th of a meter, and the 7 was a guess. So all scientists record using the same rules so that when they exchange their data, they understand what each measurement represents. So Rule 2, pretty straightforward. Sandwiched zeros are significant. Then we start to deal with zeros that are on the right side, that are to the right of a non-zero digit. Let's take a look at this number here. The 1 is a significant figure because of Rule 1. The 9 is a significant figure because of Rule 1. This 0 is significant because it's sandwiched in between the 1 and the 9. So far we have 3 sig figs. Okay? These zeros here, are they to the right of a non-zero number? Yes, they are to the right of the 9. Are they to the left of an understood decimal point? Now our decimal point would be understood to be where? Right there. But it's not written. They are to the left of an understood decimal point. So according to this rule, those zeros would not be considered significant. So this measurement, 109,000 kilometers, has 3 sig figs. Well, if these 3 zeros aren't significant, then why are they written? They're written because they have to be. You can't write 109,000 without those zeros. They are called place value zeros. Place value zeros are not significant unless something on there takes note of being significant. I'll show you that in a second. And there's a little bit of a typo here that we'll fix in a moment. 109,000 kilometers, this number takes 3 sig figs. So apparently, and maybe this measurement was taken by an astronomer, distance between 2 moons or something. It's a pretty large value for a distance. But whatever instrument they used, because this has 3 sig figs, they were sure of this 0, and the 9 was a guess. Because this 9 is the last sig fig from left to right. So I know the 9 was a guess. That was my uncertain digit. And these zeros are placed because they are place value zeros. Now, what's missing, or what should be here, is a line over this 0. There should be a line right there. So let's say this distance was measured by one laboratory, and this measurement was taken by a second laboratory. Let's give this some units too. Kilometers. Well, let's say this laboratory that took this measurement had better equipment, more accurate equipment. So when they took the data, this 0 was the last certain digit, and this 0 was guessed. Now these are still place value zeros. I already mentioned that most of the time place value zeros aren't significant, unless they are included in the certain and uncertain digits. So if this measurement was taken and the 0 was certain and this 0 was guessed, how do I show that it was part of the measurement? Well, that's what you do. You put the line over it. Now this 0, because it has a line over it, is significant. This 1 is significant. This 9 is significant because of rule 1. This 0 is sandwiched. Now, is this 0 sandwiched in between 2 significant figures? The 9 is significant, and because of this line, this 0 is significant. So this guy is significant. So 1, 2, 3, 4, 5 sig figs. Well, why is this 0 written? Because it has to be. I couldn't write 109,000 without these zeros. Okay. Another way to identify significance, let's say that I was recording this number and I was certain of this 0 and I guessed this 0, I could put a line there. That would be how many? Well, the 1 is significant, this 0 is significant because of the line. These are sandwiched, there'd be 4 there. But another way is to place a decimal point next to that 0 that's in 1's position. This is the only exception to that. I mean, I couldn't go over here and put a decimal because that would change the whole place value of everything. This would be a 10,900 instead of 109,000. So this measurement has 4, and this measurement has 4. Because according to this measurement, this 0 was a certain digit, and this 0 was the guess. So how do I show that it's the guess digit? In other words, how do I show that it's a significant figure? I put a line over it. I put a decimal there. So either one of these is acceptable to show 4 sig figs. Zeros to the right of the decimal, so notice we've moved over to the other side now. To the right of the decimal point, but to the left of a non-zero digit, are not significant. Let's take a look at this number here. We have 0.00476 There is no unit on there, but we're just saying it's a measurement. 4 is significant, 7 is significant, the 6 is significant because of rule 1. Are these zeros to the right of the decimal point? Yes, they are. Are they to the left of a non-zero number? Yes, they are. According to this rule, they are not significant. So why are they there? Well, once again, place value is because you can't write that number without those zeros there. Now, could I write this and mean the same thing? Does this have 3 sig figs? Just like this number. Yeah. 1, 2, 3. These numbers are significant because they're not 0. Where's all the place value then? Well, it's up here. If you're writing scientific notation, the exponent is never significant. All the significance is over here on the left side of the multiplication sign. So 0.00476 or 4.76 times 10 to the negative third, they both have 3 sig figs. All zeros to the right of the decimal point and to the right of a non-zero number are significant. So let's take a look at this number. The 4 and the 6 are significant because of rule 1, non-zeros. This 0 here, is it to the right of the decimal? Yes. Is it to the left of a non-zero number? Yes. So this guy is not significant because of this rule up here. Are these zeros to the right of the decimal? Yes, they are. Are they to the right of a non-zero number? Yes, they are to the right of the 6. These are called trailing zeros. And trailing zeros are always significant. And the way you think about it is, in math, when you're writing 0.046, it doesn't make a difference whether you put a 0 there or not. It's still 0.046. But in measurement, these zeros make a difference. What am I saying by putting these zeros here? I'm saying this 0 was the last certain digit in the measurement, and this 0 was the guess. So anything that you add, anything that's extra on the end of a number that's a 0 like this, is going to be significant. So how many would be here? Well, the 4 and the 6 would be 2. And are these zeros to the right of the decimal? Yes. Are they to the right of a non-zero number? Yes. So there would be 1, 2, 3, 4, 5, 6 zeros, 6 sig figs for this one. Up here, there's only 4. Trailing zeros. Counting numbers and defined constants have an infinite number of sig figs. What this means is that if I had a dozen eggs and I counted them out, I could write 12, I could write 12.0, I could write 12.000. I could write an infinite number of zeros off of a counted number and still be correct. So what we say about counting numbers and defined constants, we say they have infinite sig figs. The reason that's important is in a lot of the calculations, when you round, you're usually rounding to the least amount of sig figs. So if this has unlimited significance, it wouldn't ever be the least amount. What's a defined constant? Well, a defined constant would be something like 1 meter equals 100 centimeters. There is exactly 100 centimeters and exactly 1 meter. I could write 1.0 here. I could write 100.0. That is a defined constant. There's exactly 12 feet. Oops. Forget that. There's exactly 12 inches in 1 foot. I could write 12.0 inches. I could write 1.0 feet. I could write an infinite number of zeros and still be correct. So defined constants like 12 inches equals 1 foot, or 1 meter equals 100 centimeters, or 5,280 feet equals 1 mile, and so on and so forth. And counting numbers. You know, if you count the number of people in a room and you come up with 25, there's exactly 25. I could write 25.0. I could write 25.00. I could write 25 point and then infinite number of zeros and still be correct. Those have infinite significance. So just to sum up, the most significant figure is always the leftmost non-zero digit, regardless of where the decimal point is located. And as you go to the right, things get less and less significant. Alright, hope that clears up some things with sig figs. We'll do some practice with rounding in part 7.